Okay, let us start. It's your first lecture for third semester. I have already shared the syllabus with you in the WhatsApp group. You have 4 units in the syllabus, and we will start the syllabus with unit first. Course name of your course is Thermal Physics and Statistical Mechanics and Statistical Mechanics. Start with unit 1, which is about thermodynamics. So if we define thermodynamics, give its definition, it's defined as, say, thermodynamics is the study of energy transfers involving temperature occurring between macroscopic bodies, occurring between what happened to this? Let me set it. Alright. One minute. Okay. Occurring between macroscopic bodies. This is how we define thermodynamics. We say it is a study of energy transfers involving temperature occurring between macroscopic bodies. So we are dealing with energy transfers those energy transfers which occur between macroscopic bodies where there is involvement of temperature. Now you will be familiar with different kinds of temperature scales. We have Celsius scale, we have Fahrenheit scale, we have Kelvin scale. Temperature has a proper definition, and it is one of the base physical quantities in SI system. You must be knowing that we are not here giving the definition of temperature first. We take temperature as we measure it by thermometer. Now this thermodynamics, this study involves its own physical quantities, like we talk of heat in thermodynamics, we talk of temperature, we talk of internal energy, entropy, etc. So these are some of the physical quantities which are related with the study of thermodynamics. Thermodynamics has its own laws. We will be discussing those, like we have zeroth law, we have first law, we have second law, we have third law. In mechanics is another branch of physics which deals with study of objects in motion. It has its own laws, it has its own quantities, like we talk of force, mass, work, torque, and there are laws for studying mechanics, Newton's laws of motion. Similarly, thermodynamics is a branch of physics which has its own laws, own physical quantities. We will be dealing with these in this course. First, we start with macroscopic state variables. Macroscopic state variables. For example, I have some container. With volume V. It's kept at pressure P. In this container, I have some gas. I denote it like this. Let these be gas molecules. So I have a gas, can be any gas, with some mass, kept at certain volume V and kept at pressure P. I want to study this system. This is my system. I repeat, I have a system comprising of a gas which is kept at pressure P and which occupies volume V. Now this is my system. So inside this, there are gas molecules, and those gas molecules will be moving in different directions, colliding with each other and the walls of the container. We know the collisions will be of elastic nature. So these gas molecules will be moving, making elastic collisions with each other and with the walls of the container. Now this is my system. But to study this system, we have two approaches. We have two approaches. One is this color is better. One is microscopic method. And second is macroscopic method. Macroscopic method, right? So we have a gas kept at pressure P and volume V. Now I am saying this system can be described using microscopic method and macroscopic method. We discuss first these methods. First, microscopic method. So in this method, we have to follow all the particles, namely molecules of the gas. If we have n molecules in the gas, for example, this container contains oxygen gas and I have 32 grams of oxygen in it, and you know this is going to contain Na number of molecules. What is Na? Na stands for Avogadro's number. So it is Avogadro's number. Its value is 6.023 into 10 raised power 23. So if I have a gas, oxygen, in this container and its mass is 32 grams, then it will contain 1 mole of oxygen gas. That means it is going to contain this much number of molecules. This is a huge number. Now, if we assume only translational motion, in the gas, then each molecule can move along. This is my X, this Y, this Z. Each molecule in the gas can translate along x-axis, along y-axis, and along z-axis. That means each molecule will have velocity along x-axis Vx, velocity along y direction Vy, and velocity along z direction Vz. And it will have 3 coordinates, x, y, z. So each molecule possesses 3 coordinates, 3 position coordinates, and 3 velocity coordinates. That means each particle can move in 3 directions with the corresponding velocities. So each molecule will have 6 coordinates, 3 position, and 3 velocity. right? So I have a number of molecules. Each molecule has 6 coordinates. That means in total I have 6 times this much number of coordinates, right? That means I have 6 into 6.023 into 10 raised to power 23 variables, position and velocity coordinates. There's a huge number. You know, when we solve Newton's law, how we write Newton's law, net force on a particle is mass times acceleration. We write it as second order derivative of position with time d2x by dt2. So for each coordinate, I will have an equation and I will have to list this much number of equations. 50% of these equations will be for position and 50% of these equations will be for velocity. Now, it is impossible to even list this much number of equations. It's a huge number. If I take 1 second to write one equation, then this much number of seconds I will require to list this much number of equations, and then we have to solve them. So it's impossible. And we were only considering translational motion. Oxygen is a diatomic molecule. It can have vibrations. It can have rotations. And to consider vibrations and rotations, we will have more number of coordinates to handle with. So microscopic method, when we have to deal with microscopic method, the number of atoms is huge, number of molecules is huge. I mean, say number of molecules in the gas is huge. So that way, to follow each molecule and solve its equation of motion and to make predictions about it is impossible. So we have another method, that's macroscopic method. So in macroscopic method, we do not consider this gas at molecular level. You know, it contains molecules, they are moving, they are gliding, changing their direction of motion. But we disregard all that. We take this system in totality and consider some variables which we call macroscopic variables like pressure, volume occupied by the gas, pressure of the gas, temperature of the gas, internal energy of the gas. So these variables we call macroscopic variables, and to give description of this gas, we have to consider only these few variables. To deal with few number of variables, namely pressure, volume, temperature, it is very easy. This macroscopic method is the characteristic of thermodynamics. In thermodynamics, we take systems as whole and give their description in terms of these macroscopic variables, which are only few in number, and it becomes easier for us to give description of the system. Now, the minimum number of macroscopic variables needed to describe the system will depend on the kind of the system, but it is always a small number when compared to microscopic variable, which we discuss is huge. If we have a fixed mass of gas, fixed mass of a gas, that means mass is fixed, only two variables are required to specify its macroscopic state. For example, you can take pressure, volume, volume temperature, or pressure temperature. Any two variables suffice to specify its macroscopic state. The state specified by these macroscopic variables is called a macroscopic state. And microscopic state means the state specified by the positions and velocities of the all gas molecules present in the gas. So macroscopic method is easy. Now another thing here is thermal equilibrium. What thermal equilibrium? I mean to say, if I have a gas in a container, so it's my gas. Now it will contain certain number of molecules. It will have some volume V. It will have some pressure P. It will have some temperature T. Now, how can I assign pressure, temperature to the gas? For example, if I have a stirrer, I have a stirrer and I stir this gas. That means I unsettle the gas. What will happen if I bring a thermometer near the stirrer? Here temperature will be larger than the point which is far from the stirrer. Simply, if I make the measurement in pressure, the pressure at different locations of the gas will change from point to point and will also change in time. During stirring, when I unsettle the gas, it is impossible to assign a value of pressure at temperature to the gas. That means it is impossible to specify the macroscopic state of the gas. So what I have to do, I have to stop stirring. Let the gas settle. When the gas settles, we see this gas is now in thermal equilibrium with itself. Only then the pressure, temperature, and volume can be assigned to this gas. How we define now this thermal equilibrium? We say when the macroscopic properties, that means macroscopic properties, pressure, volume, temperature, of an isolated system. When I say isolated system, you must be knowing isolated system means that system which cannot exchange matter or energy with its surroundings. So thermal equilibrium, condition of thermal equilibrium is defined as, we say, when the macroscopic properties of an isolated system become constant in time, the system is said to be in thermal equilibrium with itself. I repeat, when the macroscopic properties of an isolated system become constant in time, the system is in thermal equilibrium with itself. Only then we can specify, assign to it the values of pressure, temperature, volume, and specify its macroscopic state. So you always remember when we say some gas is having pressure P, volume V, temperature T, we specify its macroscopic variables. It is understood the gas is settled. There is no stirring taking place anywhere in the gas. gas is in thermal equilibrium with itself. Only then it is possible to specify its macroscopic state, right? Another thing here is I write it, then I explain. There are many different microscopic states, many different microscopic states corresponding to a single macroscopic state. There are many different microscopic states corresponding to a single macroscopic state. What's the meaning of that? In this gas, let it be in thermal equilibrium with itself. So it contains gas molecules, or it has certain pressure, certain temperature, certain volume. So it has certain macroscopic state. Because these values have been specified. There is no stirring taking place. Gas is settled. We have specified its macroscopic state. But the microscopic states are changing because the microscopic state is specified by the location, the position coordinates of all the molecules in the gas and their velocities. Molecules are constantly moving, they are colliding with each other, their positions are changing, their velocities are changing. That means their microscopic states are different at different times of this gas. Microscopic states are changing. But macroscopic state is specified by PTV, that is specified, that's not changing. That means all the microscopic states comprised by different positions and velocities of all the molecules of the gas belong to this single macroscopic state, right? Then we have another idea to discuss, that is adiabatic and diathermic wall. How we define it? First, consider this observation. If I have a container containing certain gas, it contains certain gas molecules. If I heat it, I have some Bunsen burner, so I heat it. Now I can heat it in different ways. Let there be piston, and let this piston be fixed. If the piston is fixed, that means volume V is constant. So this way, if I heat this gas, keeping its volume constant, that means this piston is fixed. What will happen to this gas? Its pressure P will increase. So we say, if we have a constant volume gas system, that means a gas whose volume is kept constant, and we heat it, pressure will increase. That means for a constant volume gas system, pressure increase indicates temperature increase. You need to remember it. Another thing, another possibility is you take the same gas, now the piston is movable. This piston is movable. A piston is movable, that means P is constant. Pressure is constant. And in this sense, in this way, if you heat this gas, what will happen? Pressure is constant, piston will move, so V will increase, volume will increase. So two ways of heating the gas I am describing. One is heating the gas at constant volume, that means piston is fixed. In that case, by heating the gas, pressure will increase, that means pressure increase will indicate the temperature increase. Second situation is if the piston is movable, that means volume is not constant, pressure is constant. In this situation, heating the gas will increase its volume. That means for constant pressure gas system, volume increase will indicate temperature increase. Next thing, now if I have two constant volume gas systems, I have two constant volume gas systems. System 1 is 1 and system 2. That means I have two gas systems whose volume is constant. What I do, let the temperature be different. Its temperature T1, its temperature T2. And these two systems are isolated from their surroundings. Isolated from their surroundings. I repeat, two constant volume gas systems, two gas systems, S1, S2, at different temperatures T1 and T2. They are isolated from their surroundings. That means their temperature, whatever is, will stay constant. Now what I do, I bring these two systems in contact with each other, and the contact is my thin metal wall. I have here thin metal wall. What will happen? The temperatures and pressures of both these systems will change because they were previously at different temperatures. The pressure of one gas will increase, the pressure of other gas will decrease. Since they are constant volume gas systems, pressure increase will indicate temperature increase. That means one system whose pressure is increasing is heating with time, and the other system whose pressure is decreasing is cooling with time. That means heat transfer will take place between these two systems. And this situation will remain for some time until these systems come into thermal equilibrium with each other. That means these systems will come to thermal equilibrium with each other. That means they will attain a common temperature. That temperature will lie between T1 and T2. So what is the meaning here? Meaning is the systems were previously at different temperatures. So when I bring them in contact with thin metal wall, these macroscopic properties will change, and after some time those macroscopic variables, that means temperatures and pressures of the systems, will stop changing. When they stop changing, we say the systems are in thermal equilibrium with each other now. If previously their temperature was same, that means if this T1 and T2 were same and you bring them in contact with each other through thin metal wall, then nothing will happen. They are already at same temperature. Their macroscopic variables are not going to change by bringing them in contact with each other, right? Now, instead of thin metal wall, if between these two systems I have thick asbestos wall, thick asbestos wall. In this situation, almost nothing will happen to the macroscopic properties. The temperatures of the systems T1 and T2 will stay constant. Macroscopic variables will not change. This way, we define two types of ideal separations. One is adiabatic wall. Second is diathermic wall. What is the definition of adiabatic wall? We say two systems are said to be separated by an adiabatic wall if, on changing the macroscopic variables of one system, no change takes place in the macroscopic variables of the other system. That means if you heat system 1 and there is adiabatic wall between the two systems, it will not affect the system 2. So this adiabatic wall has a common name. It is perfect heat insulator, and thick asbestos is a good approximation of adiabatic wall. So if we have to isolate two systems heat-wise, you have to have an adiabatic wall between them. And thin metal wall is example of diathermic wall. Diathermic wall is perfect heat conductor. So here if we have two systems and there is diathermic wall in between, if you heat system 1, macroscopic variables of the other system will automatically change because heat will flow from system 1 to system 2. So when two systems are separated by a diathermic wall, changing the macroscopic variables of one system will affect the macroscopic variables of other system. And thin metal wall is good approximation of this diathermic wall. Common name is perfect heat conductor. An adiabatic wall is thick asbestos wall. If two systems are separated by adiabatic wall, you can make change in the macroscopic variables of one system without affecting the macroscopic variables of other system. So we have adiabatic wall and diathermic wall. I will give you homework. Question 1 is your homework. Question 1 is, what volume is occupied by 1 mole of gas at standard temperature of 0 degrees Celsius and normal atmospheric pressure. Question is, what volume is occupied by 1 mole of gas at standard temperature of 0 degrees Celsius and normal atmospheric pressure? Question 2. How many molecules are there in 1 cubic centimeter of gas at 0 degrees Celsius and atmospheric pressure? Question is, how many molecules are there in 1 cubic centimeter of gas at 0 degrees Celsius and atmospheric pressure? I will give you the answers. Question 1 has answer 22.4 liters. Question 2 has answer 2.68 into 10 raised power 19 molecules. 2.68 into 10 raised power 19 molecules. This is all for today. Thank you and work hard.